So the model which we have to model in Etabs is shown. It is the same model used in design of reinforced concrete columns for intermediate resisting frame. The FC prime and F5 is given. Floor height is 10 feet and is a ground plus 1 structure. The center to center span of the column is 18 feet. The slab is 8 inches thick. Live load is 40 psf. Super dead load is 20 psf. The seismic zone is 2B. The soil type is SD. The columns are 12 by 12 inches. The design was carried out in the Etabs tutorial video whose link is given in description for the columns. It is a residential building. We have to use UPC 97 for seismic loading, and the allowable bearing capacity or gross bearing capacity of soil is 5 kilo KSF. Depth of footing base below the natural ground level is 4 feet, and we have to design the isolated footing for the columns shown. We have to consider the few things for the design. Footings must be designed to carry the column loads and transmit them to the soil safely. The design procedure must take the following requirements for the strength design. The area of footing based on allowable bearing soil capacity, one-way shear, two-way or punching shear, bending moment and steel reinforcement requirement, bearing capacity of columns at base and dowel requirements, development length of the bars, differential settlement. So in this video we will be designing the footing following these safety basic guidelines to design the footing. The structure was already modeled in the video whose link is given in description for the design of intermediate moment resisting frame columns. So the section properties and material properties are defined as shown on the Etabs screen. Section properties for the frames. It's a flat plate system, so no beams are present. The correct moment of inertia modifiers for column using ACI code. I'll be showing the slab section used. It is an 8-inch slab section used, and the property modifiers were using ACI code. That is 0.25 of gross moment of inertia. The mass source will be including the dead loads and the multiplier of 1. It is a low-rise structure, so no live load inclusion is considered in the mass source. The load patterns defined are shown. The earthquake in X direction and Y direction is also shown. Let's see the modifiers and parameters set. Using UBC 97, we will be using intermediate moment resisting frame as it is zone 2B. The tables and selected parameters using UBC 97 are shown and will be input in the Etabs lateral load screen. So it's same as X, just the difference is the direction changes to Y. All the parameters remain same. The load combinations are shown which were used for design of columns. For the foundation we will be using these service loads. So I am going to add a total dead load combination, or you can say total dead load case at service stage. Similarly, a total live load case at service stage. Now select all the slabs by pressing Ctrl A or selecting the whole structure. We will be assigning the diaphragm, that is a rigid property as it is a concrete structure. Structural base is taken as fixed. It is important that you take the same condition for the supports which were used in design of beams and columns. Since the column were designed considering the base as fixed, so I am taking them as fixed again for the design of footing. Now we will run the model. Let's have a view of the structure which we have modeled. So in this video we will be focusing on typical interior columns and will design the foundation for the interior columns. Excluding the exterior columns, the design would be similar, the procedure would be similar. So we will be designing this portion of the structure for the foundation. Let's say we will be designing the interior columns footings only. So uncheck all the structure, just let the joint objects remain open. Let's hide the external columns as we are not concerned in this video to design the external column footing. The design procedure will be similar. We will be designing the interior column footing and a typical footing considering the highest forces in the columns. So for the first step we will be going for the reactions of the base on the dead load. So it is the Excel sheet I will be using for design. The link for download of this Excel sheet is given in description of the video. So first have a look on the Excel video. We will be inputting the design loads extracted from Etabs in this sheet and input the parameters and then extract the design result which will be used in detailing the AutoCAD drawing. So it is the input form which we will be extracting from Etabs. So starting with the help section, all service loads shall be taken from the Etab load cases. Etabs earthquake load cases is based on UBC 97, which is we have considered. Number 3, all load combinations using earthquake forces shall be taken Etabs auto generated or can be manually calculated. The provided factor 1.3 and 1.6 is based on wind load. If wind load are calculated by UBC, take 1.3. Program does check footing in both directions. Program divides earthquake load by 1.4 to bring them service level. Okay. All ultimate forces of the footing design are automatically calculated by program. That is okay. Number 8. Program automatically subtracts the weight of the footing and soil above to get allowable bearing pressure. Since normally the allowable bearing pressure are given in geotechnical reports, add the soil and concrete bearing pressure to the given to get cross bearing pressure. Okay. All the input in this Excel sheet is shown in blue color. That is okay. Only the absolute values for the moment in each direction for load case shall be entered in the input data. That is also okay. MD, that is moment for dead load, and ML, moment for live load, are usually small. Therefore use the largest value for both the directions. Okay, first of all, we have opened the base reactions for the dead load, which we will be giving input in the Excel sheet. So the values are shown. We will pick the highest value since we are interested in designing a typical interior footing for the interior column. The highest value was 91.05 kips. It is important to check the units before putting in the sheet. It should be in kips. Let's go for the live total and apply. Selecting the highest magnitude for the live load axial force coming on the column. The load is in service state, that is unfactored. Now going to earthquake, we have to go to plan view for the base of the structure where we assign the supports. It's your choice, you take fixed or hinge, whatever the supports were used in designing of the column. Now go to tabulated and click on Fy, Fx and Fz. Now selecting the highest magnitude of force in Ex direction with the respective sign. The highest force for the typical interior, you may also find it in X direction. Since earthquake is being applied in X, so the highest force is coming in X direction. So we will give the input of the highest force we are getting from the Etabs. Highest force was 7.341 kips in negative. Similarly, for Y direction, we will select EY, earthquake in Y direction, and select the highest force, that is again 7 point minus of 7.328 kips. Since no wind load is applied, it is a low rise structure, so we will be neglecting that. Now for the moment due to dead load, we will again go to the base reactions. Now we will be looking at the base reactions due to moments. Since our requirement is the moment due to dead load, click on reactions, select dead load, that is dead total we defined in the load case, and click on all three of the moment values. Select the highest value of the moment we are getting here. Taking the highest value as seen from Etabs, that is 0.803. And now moment due to live load, that is live total load case defined. Zero point 2677 3. Okay. Now for the moment of earthquakes, go for moment due to earthquake in X direction. We are getting 55, a value of around 55 as the highest value. Let's plug in the value. The highest value is, let's have a careful look, 55 with a negative sign. Now we'll be seeing the same reactions for the earthquake in y direction. So we are getting a similar kind of value that we were getting in the x direction. That is 55.75. Now the column dimensions used were 12 by 12 inches. So now you see the values are imported from the data sheet. The gross bearing pressure was given as 5 kilo kip per square feet. The soil density taken as 100 and the concrete density as 150. FCPAM is 4 and the FI is 60. The effective depth, let's start with, you can start with a lesser number, but it's totally up to you. The software will automatically design this value for the minimum, but for the initial iteration you need to set a value. Select the seismic zone, let's is 2 or 2B. So you can see earthquake in y direction is not incorporated, so we have to incorporate that here. We'll copy this thing here, paste it here. Just the difference is it was in J2, that is imported value now. So we have got the moments and loads imported here. For the lead load and earthquake load factors, in order to come up with the load combination to design the foundation, we have to go to UBC 97 equation number 12-5. So according to UBC 97 equation 12-5, we are getting a factor of 1.2 for dead load and a factor of 1 for the earthquake, that is ultimate factor. For service load, the sheet will divide by 1.4 in order to get the earthquake service. And using equation 12-6, we have 0.9 and 1 for the earthquake. Using node number 2, which is mentioned in this Excel sheet, we are using UPC 1997, so the factor of 1.3 will be used as shown in the help section of this Excel sheet. The footing dimension will be as square. So we will be starting with a dimension of 4 feet by 4 feet, and we will be revising, the sheet will revise itself the dimensions. The depth of the footing below the ground is 4 feet. We have to select a number of bar. So the Excel sheet input parameters are given. The gravity pressure and the pressure of gravity plus lateral is also shown in this sheet. The footing information, the footing area, moment of inertia xy, weight of footing, soil weight, uplift capacity and square size needed is shown by this Excel sheet. This Excel sheet will also show you the two-way shear calculations and the results, whether two-way shear is okay or not. It shows the ultimate shear, shear average, column dimensions, the pressure and the capacity of the footing at shear. So in it shows the shear is okay. The gravity loads and the pressure and the moments. The gravity plus wind and the gravity plus earthquake loads and their pressure, which is also shown over here. Gravity pressure plus lateral pressure. The lateral pressure will be the governing one, that is wind or earthquake. It also shows the one-way shear, that is QU average, QUX. Similarly, it checks whether one-way shear is okay along X and Y axis. Once we click start design, it will design the reinforcement. But before that, we have to input the diameter of the bar. Let's start with number 4 bar in FPS system. You see, we have selected the type of design as square. If we selected fixed horizontal dimension or fixed vertical dimension, then the sheet would have fixed the particular dimension and calculated the other dimension accordingly. So you see 5.25 feet is the dimension coming out. Governing principle is the bearing pressure. So we are requiring number 4 at 6.2 inches center to center as main bottom bar, and the distribution bar is also number 4 at 6.2 inch center to center. You can have also selected fixed horizontal dimension or fixed vertical dimension based on your constraints and location in the plan of the structure. The cover should have been specified as 3 inches, which we forgot. So the clear cover, after specifying 3 inches, we got a depth of total depth of 12 inches. So the footing height is 12 inches required. So that is the design output given by this Excel sheet. So this Excel sheet is a very useful Excel sheet when you have to design multiple footings or a single footing. It will not only design, but it will also give you the detailing and a proper understanding. You can also modify various parameters and the load factors based on the codes you use. Similarly, you can design the exterior footings by inverting the visibility option. Definitely it is very easy using this Excel sheet. You have to do nothing, just import the loads and specify the combinations based on the cases you use or the code you use. Since I use ACI and UBC 97, so I have specified those. So now we will be detailing the first, starting with the footing size, that is, let's take as 5.25 feet into 5.25 feet, and the height was 1 feet, that is 12 inches. So we are done with naming the footings name. Typical internal footing, the dimensions are shown in feet. Now we'll be labeling the reinforcement here. We have selected number 5 bar at 7 inch center to center. You can also change the number of diameter of bars based on the availability at site and design, and press on start design again in the Excel sheet. It will give you the required design within seconds. So that is a very useful Excel sheet in my opinion. You all should use it. The reinforcement main and distribution were same. So now we are done with detailing the AutoCAD drawing for the footing required. Similarly, there is an additional information. The minimum footing steel should be calculated as follows. Shrinkage steel required. AS minimum per feet 0.0018 BH for 60 KSI steel. The calculation is shown. While for the minimum flexure reinforcement required, we have to calculate the effective depth minus clear cover, that is 3 inches, and minus the bar diameter. Since we were using number 4 bar, so it is AS minimum as per flexure requirement is coming out 0.34 inch square per feet, which is higher than shrinkage steel requirement. Hence, governing is AS minimum due to flexure. So the spacing is calculated 12 times area of bar divided by area of steel. Subscribe to the channel for much more similar content coming soon. Thank you for watching.